I shared a link on Microsoft Teams. Did anyone try open this one? This directly takes you to the OneNote 5. Does it take you or no? Yes. It does? Okay, gentlemen, I want you to turn off your mobiles. Turn off your mobiles and keep your mobiles in your pockets during the class. They should not come out of your pockets. Look at the screen for your name. Ahmed. Yes. Mender. Yes. Abdullah. Ahmad Mustafa. Ahmad Ahmed. Hussein. Saud. Abdullah. Saud Abdul Aziz. Salman. Ahmad Ahmed. Salman Abdullah. Faisal Fahad. Ahmad Abdullah. Fahad Khalid. Yes. Abdurrahman. Yes. Ahmad Suleiman. Yes. Ahmad Ahmed. Ahmad Ahmed. Hamid. Yes. Yes. Ahmad Haytham. Adib. Ibrahim. Yes. Yusuf. Yes. Hussein. Hussein Abdul. Hassan. Abdul Hadi. Yes. Ahmed. Yes. Jawad. Ahmed Mirza. Yes. Abdul Aziz. Ahmed Assam. Vishal. Yes. Saad. Fahad. Abdul Aziz. Anyone who came during the attendance? Let us quickly review what we did in the previous class, and we'll almost do the same thing with the intercept today. There is nothing new in today's class. We'll repeat almost the same thing with the same concepts. Everything will be same. It's just that last time we did it for the slope. This time we'll do it for the intercept. Yes. Let me confirm. The screen is shared. The recording is, it's on. So what we did in the last class is we found the expectation of the slope, and we found that the slope is unbiased. The expected value of the sample slope is equal to the population slope. The interpretation of this thing is that if you keep repeating, taking the data from the same population again and again, and you keep finding the slope every time, on average, these slopes will be equal to the actual slope. And we also found the sampling variance of this slope. The interpretation of this thing is the sampling variance came out to be sigma square over SXX. The interpretation of this thing is if you keep taking samples again and again, these two are repeated sampling phenomena, both of the expectation and variance. If you keep taking samples again and again, every time the value of beta 1 hat will be different. Yes? So there is a variation in the values of beta 1 hat. How do you measure that variation? By the variance of beta 1 hat. So how much there will be variation among the values of beta 1 hat from sample to sample? It will be sigma square over SXX, where SXX is again a constant quantity. You are throughout, you are assuming that x's are fixed. You know them. You know the levels of x's. Some of the properties we used during the derivation in last class is that, number one, expectation or the mean and summation, they can be interchanged. Number one. Number two, the variance and summation can also be interchanged only on one condition, if the observations are independent, and usually in random samples, the observations are independent. So you can interchange the summation and variance because the covariance terms are all zero when there is independence. So these two properties you will frequently use also in beta, the derivations of beta 1 hat. So yes. Suppose these are the 5 possible values of x, right? Now, for let us say when x is 2, you think there is only one value of y in the population? No, there are many values of y here. For example, if someone has 2 reals in his pocket, how long someone can, how far someone can travel. X is the amount, Y is the distance. You can travel by using this amount. So someone can travel maybe 2 miles, maybe someone can travel 3 miles, maybe 4 miles, 2.4 miles, 2.3 miles. So for this 2 reals, there will be many possible distances you can travel, correct? So there will be a complete population of Y. Y is the distance you can travel on this amount. X is the amount you have in the pocket. Similarly, when X is 3, there will be a complete population of Y. Now, when you talk about X only, you want the summation of X. When you apply the summation of Xi, it does make sense to sum these values when you're interested in the sum, right? But when you want the expectation of Y, you will be finding the expectation of Y for a given row. You'll be finding the mean of Y or mean of any function of Y for a given row. In that row, your X will be fixed. So when you apply the expectation concept, it's in a specific row. It's for a given value of X. But when you apply the summation, you're applying the summation over the sample. And in sample, you have a number of values of X, you can sum them. So expectation is more a population phenomena. Summation is a more sample phenomena. So in sample, X is varying. But when you talk about Y, expectation of Y, you talk about the mean of Y for a given value of X. Again. You see here, when I apply the variance inside, I don't apply the variance on CI. Because CI is what? CI is all X. And when I'm talking about the variance, I'm talking about the population variance, true? So I'm talking about the variance of Y for a specific X or a specific C.
X is there.
X minus X bar.
And the other ones.
C is basically X minus X bar. So variance will not be applied because you're talking about a specific value of X. But then after applying the variance, then you are adding a downwards. You are summing downwards. Summation will apply then. So what we did is we said that if you have a summation of any function of xi, let's say ci, yi, and you apply the expectation, you can interchange the expectation and summation. Maybe in the next step, we take ci out of the expectation. We did that. I'm not interested in that. But for now, I interchanged the. Similarly, if I apply the variance, I can also interchange the summation and variance. Only if CIYI is independent of CJYJ for all ij, which means C1Y1 is independent of C2Y2, C1Y1 is independent of C3Y3, C1Y1 is independent of C4Y4, and so on. All possible pairs are independent, and they are basically independent. These are independent observations taken from the sample. They are independent. This property usually is satisfied in statistics normally, so we can use these relationships in many derivations. I'll be using these two again today. For expectation, you don't need independence. You can simply interchange. Yeah, for the variance, you need this condition, which is usually satisfied. Now, what was the pattern that we followed in case of beta 1 hat? Number one, we did three things. Number one, we proved that beta 1 hat is a linear combination of y, normal distribution. What did that prove? That proved the distribution of beta 1 hat to be normal. Number two, what did we do? We found the mean of that normal distribution. That came out to be beta 1. And third thing, we did what? We found the variance and the distribution was complete. We'll do the exact same things today with beta naught hat. So I'll start with what we did in the previous class was we said that beta 1 hat is summation ci yi, and we said that this ci is entirely a function of x, where x is fixed, ci is fixed, y is fixed times ci, which makes beta 1 hat to be a linear combination of y's. I'll do the same with beta naught hat. What is beta naught hat? Is this beta naught hat? Any questions? Any confusions? This is the formula of beta naught hat I use. What I'm going to do is, what is y bar? Y bar is summation of yi over n. Can I write that? Any problems? And then beta 1 hat, I already proved in the previous class that beta 1 hat is summation of ci yi. Any problems? And then there is x bar. Any issues? No issues? Now I'm going to write the exact same thing in a slightly different way. I'll write summation here at the start. 1 over n here minus ci x bar here and yi here. If you multiply the things inside, do you get the previous step back? Just rearranged the things. Multiply the yi inside and then apply the summation. Do you get the things back? What's the reason of rearranging the things? The reason of rearranging the things is, again, what is this whole thing? It's all a function of x again, along with n, which is again constant. This is again a constant. This is all x or n or c. C is a function of x. N is a constant itself. So all fixed. Correct? So again, we are able to show that yi multiplied by something fixed, summation, becomes a linear combination of y. So beta naught hat is also a linear combination of y, which means beta naught hat also follows a normal distribution. It's something like this. This is called the linear combination. Linear combination means you multiply a constant and add it together. So if you open the summation of that thing, call this one as A, this whole thing, because we are calling it a fixed quantity, call it AI. So it is basically A1 Y1 plus A2 Y2 plus A3 Y3 plus A4 Y4. So it's basically the sum of y's multiplied by some constants. The next step is to do what? To find the mean of beta naught hat. This is beta naught hat, true. I'll use the property interchanging the expectation and summation. And I'll use the property that this whole thing is fixed. It will come out of the expectation. And expectation will be applied on yi. What is the expectation of yi? B naught plus b1 times beta naught plus beta 1 times.
So if you interchange the summation will be the same. You don't.
Same. Both sides will be same. Interchanging, first put the expectation or the summation, it doesn't make a difference. Here is the explanation. Find the expectation value of summation of xi, for example. What is this? This is expectation of, what is summation xi? It's x1 plus x2 plus all the way up to xn. True. Now apply the expectation. This is expected value of x1 plus expected value of x2 plus expected value of xn. Now write it in a compact form, what it will be. This is the expected value of xi sum over 1 to n. True. So look at the first step and the last step now. The expectation and summation can be interchanged. What is expected value of yi? I'm using this result. The expected value of yi is beta naught plus beta 1 xi. So I'll put that one in. This is summation 1 over n minus ci x bar times beta naught plus beta 1 xi. Clear? Clear? Now there are 2 multiplied by 2 terms. In total, there will be 4 terms. I'll just multiply them. Keep the summation outside. And first I will multiply them. First multiply the first term with first term, you get beta naught over n. Then you multiply the first term with the second term of second bracket, you get beta 1 x plus beta 1 xi plus or minus plus over n. Then first term of first bracket multiplied by second term of first bracket multiplied by the first of second bracket, you get beta naught x bar ci. And the last term will be beta 1 x bar ci xi. Yeah. Yes.
Can't I just get the first two buckets out of the summation?
Summation, no. As long as there is I. As long as there is I inside the bracket, you cannot take the bracket thing out of the summation. You can take it out of the expectation though. Because for the expectation, you are talking about a single row in the population. But for the summation, you are talking about the column. Yeah. So you cannot. Summation is a sample thing. You're summing over, look here. You're summing over what? Over sample. And expectation is a population phenomena. Now apply the summation. What will happen? First term. Is there any I in the first term? It's whole constant. So when you add a constant n times, what's the result? N times that constant. Second term. Is there I in the second term? Yes, summation will only be applied on that one. So beta 1 over n comes out. Summation is applied on xi. Third term, is there I there? Yes, so beta naught x bar and summation will be applied on ci. Fourth term, yes, there is I minus beta 1 x bar. Summation will be applied on ci xi. Clear? What will be the first term? Beta naught. What will be the second term? Whatever it is. No, it's not 0. What will be the third term? This will be 0. Minus 0. What will be the fourth term? This is 1. Summation CIXI is 1. So it is beta 1 x bar. Look at these two. Both of them are beta 1 x bar minus beta 1 x bar. So what will happen? They will cancel. What will you get? The expectation of beta naught hat comes out to be again equal to beta. You failed one quantity. The mean of beta naught hat is beta naught. Unbiased, a good property. Which one? You have summation x over n. You see? in the second term.
Yeah, okay.
Summation x over n is x bar. So it's beta 1 x bar, same, both of them are beta 1 x bar. Now let us talk about the variance. The variance of beta naught hat will be the variance of summation 1 over n minus ci x bar times yi. Again, the variance is a population phenomena. It will be applied only on y, but summation is a sample phenomena. It will be applied everywhere you see I. I'll be using the property of interchanging summation and variance. So summation goes out. I have variance of 1 over n minus ci x bar times yi. How do you take a constant out of the variance? Square. So this 1 over n minus ci x bar will go out of the variance being squared. Only out of variance, not out of the summation. 1 over n minus ci x bar whole square. And variance will only be applied on yi. Yes. How can I take the ci out? The way I took there is I cannot take it out of summation. Summation for I, there is a summation. Look here. For I, there is a summation. You can't take it out of the expectation. The expectation is for a single row of x. You can't take it out. Basically, what I'm doing is there is a hidden here for a given xi. This whole thing is for a given xi. What is variance of y? Sigma square. Same as the variance of epsilon. Sigma square. So this comes out to be 1 over n minus ci x bar times sigma square. Clear? Do you see any I in the subscript of sigma square? This is where the assumption of constant variance is working. If there is no constant variance, you cannot proceed from this step. You cannot go ahead. You will stop here. And this will be the final expression of variance of beta naught hat. And same is true for beta 1 hat. We did use this constant variance and we took it out of the summation. So because it is constant, it will go out. And summation will be only applied on 1 over n minus ci x bar. Final step, I will open the square and apply the summation. So let us see what happens. First, I will open the square. 1 over n square minus 2 over n times ci x bar plus ci square x bar square. A square minus 2ab plus b square. Now I apply the summation. 1 over n square. Any n in any I in it? No, so it will be n times that constant. Do you see any I in the second term? Yes, so 2x bar over n goes out. Summation will only be applied on ci. Do you see any I in the third term? Yes, so x bar square goes out. Summation will only be applied on ci square. Any questions up to this point? What about the middle term? 0 because of summation ci. So it all comes down to this 1 over n minus x bar square. What is summation ci square? 1 over sxx. And this is what you have seen multiple times. Plus, this is what you have seen. You have seen this. This is the variance of beta 1 hat. And you have used it. So this completes the distribution of beta naught hat, which is, let me write both of them now. Now your beta 1 hat follows a normal distribution with mean beta 1 and variance sigma square over sxx. And your beta naught hat also follows a normal distribution with mean beta naught and variance sigma square into 1 over n plus x bar square over sxx. Now the distributions are complete. Now that the distributions are complete, any questions until this point? A whole new story is going to begin. If you have any questions, you can ask now. Now, let's say for a specific parameter, let's say I'm interested in the slope here. So if I want to do the testing regarding the slope, or I want to derive the confidence interval for the slope, I will convert the slope, because slope is normal, I will convert it to standard normal. I will define a z statistic for that. So the z statistic for slope will be what? The variable minus its mean divided by its square root of its variance. True? Which will not always be 0. Its mean will be 0. The mean of z is always 0, and z stays between -3 and +3. And then if you define a confidence interval for this one, what it will be beta 1 hat plus minus z alpha by 2 times sigma square over sxx whole square root. Yes? Have you seen these in any books? I'm sure you haven't. I am sure you haven't seen this. Why you haven't seen this? Because this is the correct Z formula. This is a correct confidence interval, but impractical. Why impractical? You don't have sigma square. But when you talk about a single variable case, you do see that case of known sigma in the books. Do you see or no? You see a confidence interval based on Z, and you see a confidence interval based on T. You see both of them, right? You say that usually the sigma is unknown, but maybe sometimes you have it. So when you have it, you use Z. When you don't have it, you use T. But here you start the discussion with T in stat 214 or 2 whatever, 211, 212 or whatever. You simply talk about T. Why you don't talk about Z? Because you never know sigma in case of regression. In case of single variable, maybe sometimes you know, but in this case, you never know. Why you never know? Think about what is sigma. What is sigma? It's the variance of epsilon. To start with, it's the variance of epsilon. What is epsilon? It's a variable that doesn't exist. You imagined it. You assumed it. Epsilon doesn't exist. It's the difference between the point and the line. Which line? Imaginary line. Epsilon doesn't exist. How is it possible that a variable that doesn't exist, you know its variance? So in case of single variable, you give a very careful statement that sigma square is rarely known. Rarely means 1 out of many times. But here you can comfortably say that sigma square is never known. It's never known. And hence, these formulas are completely impractical. Completely impractical. Suggesting a single solution. What is the solution? Get it estimated. Get it estimated from the sample. Now, how do you estimate it from the sample? I take you back to the single variable case. Now, when you have a single variable, in case of single variable, how do we estimate the variance? We take summation of the variable minus its mean whole square divided by n minus 1. What is this n minus 1? Degrees of freedom? Degrees of freedom? What is the logic behind this degrees of freedom? It's actually you are losing each degree of freedom against any other parameters you are estimating. Now, in case of s square, you are using an estimate of another parameter. What is that? Look at inside the formula of s square. There is an estimate of another parameter. There is mu. There is another side parameter that is also unknown. So for that mu, the another parameter that you are also estimating, you lose 1 degree of freedom. So it becomes n minus 1. If it were 2 parameters, you would lose 2 degrees of freedom. If there were 3 parameters, you would lose 3 degrees of freedom. It would be n minus 3 and so on. So it is basically n minus the number of other parameters you are estimating and using inside the formula of s square. This one. You are plugging in the estimate of mu here, right? If it was summation of xi minus mu whole square, you would have divided by n straight away. The degree of freedom would be n straight away, not n minus 1. Now let us go back to our case. In our case, what is sigma square? Sigma square is the variance of epsilon, right? Do you have epsilons? Do you have them? You don't have them. What do you have? You have their estimates. What are they? EIs, residuals. You have EIs. You don't have epsilons. You have EIs. The sample residuals, right? So you will define the formula of variance for sample residuals. It will be EI minus E bar whole square over what? N minus 1 or what? For finding these E's and E bars, how many other parameters are you estimating? 2. You are estimating beta naught and beta 1. To get to these EIs, what are EIs? It is yi minus yi hat, true? And what is yi hat? It is beta naught hat plus beta 1 hat xi, true? Right? So to get to these EIs, you need these two. These are the two you are plugging in. So against these two, you lose 2 degrees of freedom. So it will be n minus 2. Have you seen this formula somewhere? You haven't. You haven't. You have seen a simplified form of this one. How? I'll do a little more, and then you will agree that you have seen this formula. What is E bar? It is sum of EI over N, right? What is sum of EIs? Yes. EI is YI minus YI. You can do it. Let me make it like this. E bar equals 0. And the deadline is Saturday night. What is the date? I will post this thing on the Blackboard. This box will be on the Blackboard today with the name assignment number 1. And what you're supposed to do is you're supposed to do this maybe 3 or maximum 4 steps derivation to prove that E bar is 0. Scan it and upload it onto the Blackboard. Maximum, I think 3 or 4 steps, no more than that. Now, because E bar is 0, the mean of residuals, last time I showed you in Excel that E bar is 0. The mean of residuals or the sum of residuals was 0 when I applied it on Excel. I showed you it was 0. You have to prove it, not show it. So when E bar is 0, the formula becomes what? This formula becomes simply summation EI square over N minus 2. Clear? Clear? What is summation EI square? It is the sum of squares of errors. It is the sum of squares of error, true, which is abbreviated as SSE. What happens when you divide the sum by the number? It becomes, sum becomes mean. So as a whole, you call it MSE, which is mean square error. Have you seen this before? Yes, you have seen this before. This is the estimate for sigma square, or you can say the square root of mean square error is the estimate for sigma. When you plug this thing back into the formula, Z becomes T, and the degree of freedom becomes N minus 2. And we get T equals beta 1 hat minus beta 1 over MSE divided by SXX square root. And also you will have beta 1 hat plus minus T alpha by 2 with V degrees of freedom times MSE over SXX. Similarly, for beta naught hat, you will have beta naught hat minus beta naught over MSE times 1 over N plus X bar square over SXX. And you will have beta naught hat plus minus T alpha by 2 with V degrees of freedom times square root of MSE into 1 over N plus X bar square over Sxx, where for both of these, B is n minus 2. Have you seen this before? Yes, we have seen this before. In any of the service courses you took, this is what you have done. In Stat 212, you have done this in chapter 12. Stat 212, you have done this in chapter 12. In Stat 201, you have done this in chapter, I don't remember. And in 214, same book is followed, so you have done it in chapter 12 also. 12 or 13, I think, 12 or 13. Any question up until this point? Next class, I will implement this one and I will test hypothesis related to beta naught and beta 1, and I will create the confidence intervals that you have already done. Yes. Yes. Next class, you will be implementing these formulas on real applications. In case anyone has any questions, you can ask. Otherwise, you can go, and I'm going to upload the assignment now.
Using the last two formulas, I will approach the same answer.
Using the last two formulas?
Yeah, I will approach the same answer.
Which
Because
two?
T equal T equal.
No. This one is related to the intercept and this one is related to the slope. If you want to test anything about the slope, you will use this. If you want to test the intercept, you will use the second one.
So actually,
Wait.